Hi everyone, my name is Andrew Serrazina. I'm an FAA certificated flight instructor, and today I'm going to be covering the pitot static system. We're going to kind of do a deep dive into the pitot static system, how it works, the different components, the different instruments, and make sure that you have a good comprehensive understanding of the pitot static system. I want to kind of break down a quick myth because people think it's like super complicated. It's really not that complex of a system. There's, obviously 3 different instruments, and there's really 2 different principles or inputs to those instruments that we're concerned with when we're dealing with the pitot static system. So it's not something to get super scared of or super worked up about. It's a super simple system, and we're going to break it down step by step of how we go from air pressure to seeing our needles move on our airspeed indicator, our altimeter, and our vertical speed indicator. And we're going to start by clearing my screen, obviously. We're going to be discussing the 2 different air inputs per se that result in the inputs on our pitot static system. We have ram air and we have static air. Now you might be asking what these mean, and I'm going to focus here starting on ram air. Ram air is also called dynamic pressure. That's another term we can use for ram air. But the general gist is what's happening is we have an instrument, or a device rather, on our wing, which is called a pitot tube. And it's usually that gray tube that kind of drips down and comes forward, or on Pipers it just kind of comes straight down and it's got a slight curve on the backside. That's our pitot tube, or our pitot mast. And what we have is a very small hole in the front that allows air to enter. Now, there's this little chamber inside here where that air is going to enter into. Actually, the chamber's going to extend kind of all the way up here. We'll get there in a little bit. I want to focus on kind of what's happening right here at the entrance. I'm going to use a different color, use red. Right there at the entrance, air is being allowed in. So what is happening is that as our airspeed is increasing, air is passing over our wings quicker. The pressure and the force that air has as it's hitting and entering the pitot tube is going to be higher. The pressure as that air is entering into our pitot tube is going to be higher as it's moving quicker, which seems counterintuitive to how we describe lift and Bernoulli's principle. But what's happening is because the air is just being forced in, that's what we're measuring, is how that air is being forced. That's the pressure. It's not to do with high pressure and low pressure and so on and so forth. It's just very simply as that air is moving faster, it has a greater force as it's impacting our pitot tube, and that is what is going to cause us to have a higher pressure as we move quicker through the air. So I want you to remember that principle is as our airspeed is increasing, our pitot pressure is going to increase. So I'm going to go right down here. As airspeed increases, ram pressure increases. That's the super simple breakdown of our dynamic pressure, or our ram pressure. As airspeed is increasing, our ram pressure is increasing. Now, more specifically, on the pitot tube or the pitot mast itself, we have a little drain hole, which allows for any contaminants, water and stuff, to exit out to prevent it from clogging up our instruments, because obviously that would not be good. And we'll talk about pitot static blockages in a little bit. But the blockage, the purpose of that drain hole is to prevent any blockages from forming in the first place. And it does a fairly good job overall, I would say. That's our ram pressure. Now I'm going to shift and kind of talk about our static pressure, which I think is a lot simpler to understand. And I'm just going to use a red kind of circle here. As we've got on our Pipers, as we said, we've got this kind of shape like that for our pitot mast. There's a little hole on the back. That's going to be where our static pressure is. But on our Cessnas and some other types of aircraft, I flew Pipers, I trained in Pipers, I fly Pipers for the most part. I've flown Cessnas every now and again, but I'm much more familiar with the Pipers. But on the Cessnas, there's a separate system. I believe it's on the left side of the empennage, near the aft of the aircraft. And that's going to be where we get our static pressure from. And all static pressure is very simply the ambient air pressure. So they wanted to place the static port in an area where it's not going to be impacted by air flowing over the airplane. Like with our pitot tube and our ram air, we want to feel the force of that air as it's passing by our aircraft so we can get a measurement of that pressure. But our static air, we just want the pressure at the altitude that we're at. We just want whatever the ambient pressure is at the altitude that we're at. So depending on the aircraft manufacturer, they can put it in a few different places. But it's simply just a measurement of the ambient air pressure outside the aircraft. These are the two principles that fuel our pitot static system. Pitot because we have a pitot tube or a pitot mast, and static because we have a static port, or on either our pitot mast or a separate static port. That's where the name comes from. Pitot static. Those are the two ports or inputs that we're getting into the system. And this is kind of that broken down here. So what we're going to do now is kind of shift gears, and we're going to transition into each of the three instruments of the pitot static system. And we're going to start with a discussion on the airspeed indicator. I get my thick line. Nope, not quite that thick. Medium thickness. Airspeed indicator. Some people like to teach with slides. I tend to prefer to draw things out because I can articulate my thought process better if I'm able to draw than have to program a bunch of lines and stuff to show up on a screen. It's just I prefer it this way. So hopefully, please let me know down below if this is easier for you all or whatever's easiest for you, because at the end of the day, this is all about you, the students. So, our airspeed indicator, wow, that was a horrible line. I'm going to draw a box. And then I'm going to draw another little box on the inside. And I'm going to give this little box here a label. And we're going to call it a diaphragm. That's a really bad M. I can make that a little bit better. So that's a diaphragm. And what that means is that there's air that's going to be coming into the diaphragm. There's air that's allowed to enter and exit the diaphragm. So versus an aneroid wafer, which we'll talk about, our altimeter, which has a constant pressure. So, as I just said, there's going to be air entering into that diaphragm. And that's going to be our ram air, which I'm going to depict in blue. So ram air is going to be coming here into that diaphragm. And then our static air, which we said is coming from our static port, is going to enter the casing around the diaphragm. And what that's doing is it's creating a difference in pressure, assuming we're moving. Because if we're just parked up on the ramp, assuming there's no wind or anything providing any sort of alternate airflow, our ram pressure and static pressure is going to be the same. And what that's going to give us is an airspeed of 0 because the pressure is the same. However, when we start to increase our airspeed increase, we'll draw a little table. Ram and static. Our ram pressure, let me actually make this a little nicer too. Our ram pressure is going to go up, and our static pressure is going to stay the same. And what's that going to look like on our diagram up here? Well, very simply, the pressure in here is going to be getting greater. Ooh, that was weird. All right, whatever. Therefore, the diaphragm is going to expand because the pressure inside of that diaphragm is getting higher than the pressure on the outside, so it's going to want to expand. And what it's going to do is it's going to move the needles on the front of our airspeed indicator. I'm going to sneeze in just a moment. Bless myself. Thank myself. It's going to cause the needles to show that we are accelerating. And vice versa, as airspeed decreases, that ram pressure is going to drop, and our static pressure is going to stay the same. And what that's going to do is it's going to cause our pressure here, or cause the diaphragm rather to contract, which is going to have the opposite effect on our airspeed indicator and show that we are decelerating as those two pressures get closer together. So very simply what's happening, as our airspeed increases, the ram pressure is getting greater relative to the static pressure, which is causing that diaphragm to expand, which is then moving the needles on the front of the airspeed indicator that we're looking at to show that we are increasing in airspeed. And vice versa, as we decelerate, ram pressure is going to decrease closer to the static pressure. And the ratio per se is going to decrease. And that's going to cause the diaphragm to contract, showing our airspeed needle to be decreasing. So that right there is the principles that our airspeed indicator operates on. It's a very simple mechanism, as we said. And now we're going to kind of shift gears into the altimeter. I'm just going to write something down really quick. I'm going to erase this now. Hopefully everybody's, if you want to grab a screenshot, now's your chance. 3, 2, 1, it's gone. Just kidding. Well, I mean, I'm not kidding, but, you know, it's not the end of the world. Ooh, that was a little laggy. All right. Now we're going to talk about the altimeter. The altimeter operates very much the same way as the airspeed indicator, which sounds really weird when you just kind of say it that way. But I'm going to show you why. Is inside of our altimeter, we have an aneroid wafer. And I mentioned that earlier. The aneroid wafer just simply means that it's sealed. So there's no air coming in or out. And that aneroid wafer is pressurized to 29.92 inches of mercury of pressure. And I'm just going to label this really quick. Aneroid wafer. So there's no air coming into or out of that aneroid wafer. What is happening is we have static pressure coming in and filling up the area around the aneroid wafer. And what that's going to do is create a pressure differential, just like we discussed before with our airspeed indicator. It's just creating a difference in pressure. So what's going to happen is, as our altitude increases, I'm just going to do a little static and then aneroid. Draw the little T-table. As our altitude increases, our static pressure is going to drop, but our aneroid pressure of 2992 is going to stay the same. Now, what does that mean? Pressure inside of the aneroid wafer is going to be increasing relative to the static air, which is going to cause the aneroid wafer to expand. Which, again, the same principle as the airspeed indicator, as we said. It's just going to cause those needles to move to show that we're climbing, show that we are ascending. And vice versa. As our altitude decreases, static pressure is going to increase, the aneroid pressure is going to stay the same, and it's going to cause the pressure on the outside is getting closer to that 2992. It's going to push and squeeze that aneroid wafer in, causing it to contract, which is then going to show us to be descending. Now you all might be asking, great, 2992, what if we have non-standard pressure? What if we, the ATIS said 3015? The inner workings of the altimeter do not compensate for non-standard barometric pressure. But we have that little window where we can put in the barometric pressure, and you're probably wondering, what does that mean? What does that do? And that little window is called the Colesman window. And all that's actually doing is it's just moving the needles. It's literally just adjusting the needles. There's a series of gears on the inside that are programmed a certain way to adjust it a certain amount based on the pressure change. But all it's doing is moving the needles. The inside of that altimeter does not compensate for barometric pressure. It's set to 992 and the static pressure changes. We compensate for barometric pressure by adjusting the needles with that Colesman window. So that's an important distinction to make, and that's a common trip up I see with students and examiners, is that the altimeter itself does not compensate for barometric pressure. It's that Colesman window, and all that Colesman window does is move the needles. So that's a fun little tidbit to know about the Colesman window and kind of how the altimeter compensates for different barometric pressures, or rather how it does not. The inner workings of the altimeter, rather. It's just those needles that Colesman window and knob is moving. So that is going to be our altimeter. Just writing something down so I can put the timestamps down. Altimeter. Going to erase that. And now we're going to talk about what I think is probably the most complicated, and I don't even want to say complicated, instrument that we're going to discuss, which is our vertical speed indicator. And our vertical speed indicator, we have a diaphragm, which means we know that air is going to be entering and exiting that diaphragm versus a static set pressure, just like our anode wafer. And you're going to see something that's going to make you go, that's weird, in just a minute, if you're not familiar with the system, which I'm assuming you're probably just figuring this out for the first time. Maybe you want a refresher, but besides the point, we're going to dive into it. We're going to have static pressure coming into the diaphragm and static pressure coming into the casing. And you're probably wondering, and rightly so, how is that going to cause anything to change? We've got the same pressure in the diaphragm, out of the diaphragm. How is that going to cause us to see if we're climbing or descending? And there's a very clever little thing that they did, and I'm going to show you. They put a little hole in the diaphragm called a calibrated leak. Calibrated leak. And it is about 6 to 9 seconds. And what that means is, so we've got, let's say, boom, we've just started putting air in here. We're just putting all this air in at once. We've got a bunch of air out here, and we've got a bunch of air in here. The air coming into the outside of the casing, we're going to call live air. And the air coming into the diaphragm, we're going to call delayed air, in quotes. Because of that calibrated leak, the air inside of the diaphragm is about 6 to 9 seconds old, per se, compared to the live air on the outside of the diaphragm. And what that's going to do is create a pressure differential from what the static pressure was 6 to 9 seconds ago to what it is right now. Super duper simple. All that's happening is air is leaking out of the casing, or out of the diaphragm, 6 to 9 seconds after it went in, versus static air on the outside of the casing being live. And what that's doing is, let's just say if we're climbing, we're going to climb, the air on the outside is going to be a higher pressure than the air on the inside. Going to cause the diaphragm to contract, going to show that we're going to climb. Vice versa, if we're descending, the air on the inside of the diaphragm is going to be a higher pressure than the air on the outside, causing it to expand, going to show that we're descending. That's like literally the most complex part of the pitot system, is the VSI, in my opinion. And what we're going to do is, I'm just going to drop a little chart as altitude increases. Well, yeah, we'll drop. My cat just made the cutest noise ever. Sorry. And I'm going to use those same terms of live and delayed, because I think that's kind of a good way to explain it. The live pressure is going to decrease, and the delayed pressure is going to stay the same. And what we said is that live pressure being lower is going to cause the delayed pressure to expand, because it's going to be a higher pressure. It's going to show that we're on a climb. So the live pressure is going to be lower as we're climbing. The delayed pressure is going to be relatively greater than the higher pressure on the outside, or the lower pressure rather. And that's then going to cause the diaphragm to expand, showing that we're at a climb. Super duper simple. And vice versa, as airspeed decreases. Or sorry, as altitude decreases. Goodness. As altitude decreases, the live pressure is going to increase. The delayed pressure is going to stay the same. That live pressure on the outside here is going to be higher than the delayed pressure on the inside of the casing. It's going to cause the casing to, or the diaphragm to compress. It's going to show that we're on a descent. Pitot system is not that complicated. It's really, when you start to break it down, this I'd say is the most complex part, is understanding that calibrated leak and how that creates the pressure differential. So, those are our three different instruments. And I'm just going to put a timestamp down for myself. Now we're going to cover the different errors that we can see in our pitot system, which this is a super common Checkride question, especially at the instrument level. Even at the private level. Pitot static errors. And I like to teach it kind of just with a table. I'm not a huge fan of using tables, but I think to list them all out, to put it in a table and then understand why that's happening. And we're going to kind of dive into that. So I'm going to go ASI, alt, VSI, bam, bam. And we're going to start with if we have a ram blockage with the drain hole open. I'm just going to use a smaller one. Ram blocked, drain open. I'm going to make this really easy for us. Does the altimeter or the VSI use the ram port? Not applicable. Not applicable. How does it impact the airspeed indicator? Well, let's take a look and let's find out. I'm going to come down here, I'm going to draw it out. We've got our pitot tube, horribly drawn, mind you. And we said we've got a blockage. Let's say like up here. That's all blocked now. So what's going to happen is all of the air is going to come out through the drain hole. There's no air. There is no ram pressure, which means all there is static pressure, which means the ram pressure that our airspeed indicator is receiving is going to be equal to static pressure. Airspeed, let me grab the smaller or thinner one rather. Airspeed is going to be 0. Super duper easy. Now, if our ram and drain are blocked, kind of draw another one across here. Once again, we know our VSI and our altimeter don't use the ram port. Not applicable. But now let's come back to our drawing. And I'm just going to kind of touch it up here a little bit. Fix it all back together. Or let's say, yep, so both our drain and our ram port are blocked. The pressure, the ram pressure that our ASI is receiving is going to be whatever it was at the time of the blockage. So what's going to happen is our our ram pressure, I'm going to draw another table here. As our altitude increases, our ram pressure is going to be the same, and our static pressure is going to drop. What's that going to do? It's going to create a differential in pressure. So the ram pressure is going to be the same. The static pressure is going to drop. That's going to create a larger difference in pressure. Therefore, airspeed is going to show higher. And the opposite is going to be true if we descend. As alt decreases, we said that ram's blocked. The static pressure is going to increase, which is going to bring it those pressures closer together, and that airspeed is going to get lower. So the ASI essentially functions, in principle, as an altimeter when we have a ram blockage. So I'm just going to draw that in. As alt increases, airspeed increases. As alt decreases, airspeed decreases. Now we're going to get into our next blockage. Now this is one we know is going to impact all three. So we got to kind of logic our way through this, and we're going to start. I think my roommates just got home. I'd be inclined to think that. I don't know if you can hear the dogs. I apologize if you can. But continuing. Our static. Just going to draw this kind of across here. Let's start with our altimeter, because I think it's going to be easiest. Our altimeter, we know we have static air, and then we have 2992. So as our altitude increases, static pressure is going to be the same, and we know that our 2992 and our anaerobic pressure is going to be the same. Therefore, our altitude is going to be frozen at the altitude where the blockage happened. And our VSI, we know, depends on our static pressure. So if we don't have any static pressure, our static pressure is not changing, there isn't going to be any pressure differential in our VSI, because we're going to have the same pressure in the diaphragm as we do on the casing outside of the diaphragm, because it's just going to be stuck to whatever the static pressure was at the altitude where the blockage happened. So our VSI is going to indicate 0, because those pressures are just going to equalize between in and out of the diaphragm. Now, airspeed indicator, this is where it gets fun, because it's going to be the exact opposite of a ram blockage. And I'm going to tell you why. I'm going to walk you through this together. I'm going to draw our little table again. And this one I'll use our colors, ram, static. And I'm just going to go boom, boom. As, we'll say, altitude increases, our ram pressure is going to decrease, and our static pressure is going to stay the same, which means that we're going to have a lower differential of pressure between the static and the ram pressure, meaning our airspeed is going to show a decrease, or we're going to be decelerating. If our altitude decreases, the ram pressure is going to increase. As we get lower, we know that the air density is going to get greater, so on and so forth. We're going to have a higher ram pressure. But the static pressure is going to be the same. It's going to reduce that pressure differential and show that we are increasing airspeed. So as altitude increases, airspeed decreases. And as altitude decreases, airspeed increases. Now, as we said earlier, we have that alternate static that we can use. When we're using alt static, the pressure inside of the cabin is going to be slightly lower than the pressure on the outside of the aircraft. So what's happening is we're getting a lower pressure reading on our static pressure, which we know is going to show us to be higher in altitude. We know the pressure decreases the higher up we get. So our altimeter is going to read slightly higher. Our vertical speed indicator, as we know, there's going to now be a slight difference in pressure between the diaphragm and the delayed air and the live air, because the live air is going to have a lower pressure than the inside of the diaphragm is going to have a higher pressure, which is going to show us temporarily in a climb. Then 0, because it's going to go back to giving us that same pressure once it stabilizes. And our airspeed is going to read slightly faster. Because the pressure is lower inside, the static pressure is lower inside of the cabin than it was on the outside. There's now a greater pressure differential. The ram pressure stayed the same, but the static pressure has dropped slightly. So our airspeed is going to read slightly faster than it would under alt static. So those are our pitot-static blockages that we're going to see. We've got if the ram port's blocked with the drain ports open, if the ram and drain are blocked, if we have a static blockage, and what happens if we decide to use alternate static. Very simply put, that is our pitot-static system. That's what you need to know about the pitot-static system, whether it be at the private instrument or commercial level. Fairly in-depth, comprehensive overview. If you have any questions about the pitot-static system, anything that we've covered, please feel free to drop it down in the comments below, and I'd be happy to answer them. And if you enjoyed, found this useful, leave me a like, comment, subscription, any of the above would be greatly, greatly appreciated. With that said, I look forward to seeing you all in a future little webinar video tutorial explanation. And yeah, I'll see you all then. Thank you for watching.